Okay, so let's look at the solution to determining the power that's necessary for Lance Armstrong to maintain his bike velocity at 32 kilometers per hour, basically overcoming the drag force due to air acting on his body and on the bike. Okay, so if we pull up our lecture notes that can be found on Blackboard, we can see example 2.2. We have the knowns are 32 kilometers per hour for the velocity. Coefficient of drag is given to us 0.88. The frontal area was 0.36, and the density was 1.2 kilograms per meter cubed. Our find, we're looking to find the power, or W dot, and we have a schematic, sort of a poor drawing there, but essentially what we're trying to show is that there's an area that's being affected by the air that's blowing over it, and that area is causing a drag force that Lance Armstrong must overcome to maintain his speed. We're going to assume that the air is standing still, so we're going to assume that there's no headwind, wind acting on the front or tailwind. So essentially, air standing still. The drag is simply caused by the velocity of the bicycle and Lance Armstrong moving through the air, right? We were given the equation. The drag force is equal to 1/2 times the coefficient of drag times the area times the density times the velocity squared. So let's look at our analysis. If we look at one of the previous slides, we know that work rate is equal to force times velocity. So that means we can take the drag force equation that was given to us and multiply it by velocity. In that case, we'll end up with 1/2 times coefficient of drag times area times density, and here you can see we have velocity cubed. If we plug in our values, we end up with 1/2 times 0.88 times the area is 0.36 meters squared, and then we have 1.2 kilograms per meter cubed as the density. The velocity is 32 kilometers per hour, which we're going to have to convert into meters. So a quick note here is that this all of this is contained within the cube, right? So we're going to say 32 kilometers per hour. 1 kilometer is equal to 1,000 meters. All of this value will be cubed, so essentially 32,000 meters per hour will be cubed, and we end up with a value where our work rate is equal to 6.23 times 10 to the 12 kilogram times meter squared over hour cubed. Now, we want our units to be in kilogram meter squared per second cubed, which is the base units for watt, so we need to convert from hour to seconds. So here we have 1 hour. Now remember, this is cubed, right, because we have cube down here. So 1 hour cubed is equal to 3,600 seconds, and we got to cube that whole thing, right, on the denominator. So we end up, once we cube that and divide this value by that 3,600 seconds cubed, we end up with a value where the work rate is equal to 133.5 kilogram times meter squared per second cubed, which are the base units for watt. So a quick note here is what that value actually tells us is that Lance Armstrong has to continuously pedal with a power of 133.5 watts just to maintain his speed of 32 kilometers per hour, right? So that's just overcoming the drag force due to the air blowing over his body and over the bike. If he wanted to increase his speed, he would have to have a higher power, or obviously if the speed were to decrease, he could lower the amount of power. But that's the minimum amount of power that's necessary to maintain his speed. Now this is not taking into account any headwind or tailwind. It's not taking into account any. It's assuming a level road, right? So we're not going uphill or downhill. But yeah, so there's the final answer.